Hey everyone, welcome back, and thank you for joining us again in our next discussion of statistics. Heading into our objective, we're going to discuss the addition rule for disjoint events, which means we first need to discuss what are disjoint events. Disjoint events are two events that have no outcomes in common. We also call these mutually exclusive events. We're going to use a Venn diagram to illustrate this a bit. A Venn diagram is a diagram used where events are represented by circles enclosed in a rectangle. The key idea here is the rectangle represents the sample space and each circle represents an event. So let's head over to the example to elaborate on this a little bit. We're working with the addition rule for disjoint events again. We're told, for example, suppose we randomly select a chip from a bag where each chip in the bag is labeled 0, 1, 2, 3, up to 9. Now we're thinking like poker chips, not potato chips, just to be clear. First we're told let E represent the event that we choose a number that is less than or equal to 2. And then let F represent the event that we choose a number greater than or equal to 8. So we're going to bring back that image of the Venn diagram to give us a visual. And you see event E is in purple and event F would be in green to separate those. The big idea here, back to the definition of disjoint, we see that events E and F have no outcomes in common. E is that we're going to randomly select a chip that's labeled 0, 1, 2, while F is labeled 8 or 9. Those have no outcomes in common, therefore we know that we have disjoint event. So in part A we're asked to find the probability that event E occurs. The probability that event E occurs then makes us think about, well, how many options are there? We've got 3 different options here in event E that are 0, 1, and 2 out of the total number of chips that we have, which is 10. So the probability would be 3 out of 10, or as a fraction, 3 over 10. We can leave that as 3 over 10 or call that a 30% or a 0.3. We're going to leave it as 3 over 10 for now. Going over to event F then. The probability of event F is determined by saying, well, how many different ways can event F occur? We've got 2 different options, 8 and 9 for event F. Again, out of a total of 10 chips, therefore the probability that event F occurs would be 2 out of 10. Or of course that's equal to 2 over 10. We're not going to leave our answer as 2 over 10, instead we'll reduce that to be a 1 over 5, and we have our probability. Then it takes us to part C where we're asked what's the probability of either E or F occurring. Since they're disjoint events, we're able to say, well, event E has 3 different outcomes, and event F has 2 different outcomes that can occur. So altogether we've got 5 different things that occur for E or F. Therefore, our probability would be 5 over 10. Of course, we can call that 1/2 or a 50% chance of occurrence. That takes us to our next example, where we're again working with the addition rule for disjoint events. This time we're given a probability model, and it shows the distribution of the number of rooms in housing units in the United States. First, we're asked to verify that this is a probability model, like we discussed previously. Notice that all probabilities are between 0 and 1 inclusive, and if we're to add all the probabilities up, and you trust me, we'd end up with a total probability of just 1. So we're all set on the probability model. For part B, they ask, what is the probability that a randomly selected housing unit has 2 or 3 rooms? So I'm going to write this as we're looking for the probability that we end up with 2 or 3 rooms going on here. Now before we get into how to find the probability, we have to recognize that these are disjoint events. So what makes it a disjoint event? Again, all based on the definition. The definition of disjoint event is that 2 events have no outcomes in common. If we're looking at these houses, each category has no outcome in common. If I'm looking at the 2 categories that the question's asking about, where we have 2 or 3 rooms, there are no outcomes in common. If we have a 2-bedroom house, it is completely separate from a 3-bedroom house, and we have no occurrence where a 2 or 3-bedroom house can have an outcome in common. If we try to say that we've got a 2-bedroom house or a 3-bedroom house, and we try to overlap those, we would call that a 5-bedroom house. Therefore, these categories are disjoint. The difficult part at the moment, though, would be to recognize the idea of disjoint doesn't necessarily have anything to do with math. Instead, it's all on the topic and context of the question, as opposed to just thinking about it in a mathematical sense. Since we recognize that these 2 events are disjoint, that allows us to simply say, well, to find the probability of 2 or 3, we need to find the probability that a randomly selected house has 2 rooms, and we're going to add that to the probability that a randomly selected house has 3 rooms, but we get to handle those separately. We're given from the table that the probability of 2 rooms would be a 0.032, and the probability of 3 rooms would be a 0.093, Adding those two probabilities up together, we end up with a 0.125, and we've got our probability. So let's continue this over to part C then. We're asked, what is the probability a randomly selected housing unit has 1 or 2 or 3 rooms? We get to take the same logic we've already addressed, that these are disjoint events, which means as we try to find the probability of 1 or 2 or 3, we know that will be equal to the probability of 1 plus the probability of 2 plus the probability of 3 separately. Again, pulling from the table, the probability that a randomly selected house has 1 bedroom is a 0.010. And then again, as we did previously, the probability of 2 rooms would be a 0.032, and the probability of 3 rooms would be a 0.093. If we add all those probabilities up, we end up with a total of a 0.135, and that would be the probability of having 1 or 2 or 3 rooms upon our random selection. Now, trying to make the connection between our examples and the probabilities that we found and the idea of the addition rule for disjoint events, we're asked, so what is the addition rule for disjoint events? That is, first of all, disjoint events mean that if E and F are disjoint, then we get to use the rule that the probability of E or F, like we just did, would be the probability of E plus the probability of F. And this is a pretty powerful aspect. It allows us to handle the probabilities individually and add them together to find the overall probability. Note that this can be applied to more than 2 disjoint events, like we just did with the 1, 2, or 3 rooms, as long as each have no outcomes in common. And that means if we have the probability of E or F or G or etc., that simply becomes the probability of E plus the probability of F plus the probability of G. And that would just continue for however many disjoint events we have. Now that takes us to our next objective, which would be the general addition rule. We're jumping right into an example again, where we're presented. Suppose we are drawing a single card from a standard 52 card deck of playing cards. Now we've been given the entire sample space to make this a little bit easier visually. Part A asks, find the probability that we draw a 7 or a heart. Trying to build from previously, we're looking for the probability that we have a 7 or a heart. And a lovely heart we have. Remember, the first question we want to ask, though, when we're presented to find the probability of a 7 or a heart is, are these two events disjoint? So the first thing I'm looking at would be all the hearts that we have, and the next thing to discuss would be looking at all the 7s we have. Now the issue here would be that we end up with the overlap that we have, that would be the 7 of hearts, meaning we've got an outcome here that would be in both events, 7 and also a heart. So let's break this down. First of all, the probability of pulling a 7 would be 4 over 52, because we've got 4 7s that we see there outlined in green. So I can say again, the probability of drawing a 7 is 4 out of 52. And then looking at the probability of drawing a heart, we've got 13 hearts total out of our 52 cards, so the probability of pulling a heart would be a 13 out of 52. Now if we use the same logic as we did previously, then that means we'd be saying, okay, the probability of drawing a 7 or a heart would be the probability of drawing a 7 plus the probability of drawing a heart. However, the issue here we have to deal with is we've got this idea of double counting, meaning thanks to that 7 of hearts, we have to worry about the idea of double counting. So we're actually going to subtract the probability of that idea of where we had a 7 and a heart, which means the probability of drawing a 7 was our 4 over 52. The probability of drawing a heart was 13 over our 52. And we have just one 7 of hearts in order to find our overall probability of drawing a 7 or a heart, which means we end up with a final result of a 16 over our 52. Continuing on to part B now, we're asked to find the probability that we draw a red card or a jack. So just like we did before, I'm going to say we're trying to find the probability that I want a red card or a jack. So by that same logic, we recognize we're looking for a red card or a jack, and our first question should be, are these events disjoint? Going back to our sample space, let's highlight the events we're discussing. We're looking for a red or a jack. And as we take a look, it does not appear that these events are disjoint, because we see that we have 2 jacks that are also red. We've got the jack of hearts and the jack of diamonds. Therefore, we do have 2 events that are not disjoint, so we just have to adjust our math for the double counting. That means to find the probability of drawing a red or a jack, we need to find the probability of drawing a red. We're going to add that to the probability of drawing a jack, and then we're going to subtract whatever we have that is a red and a jack. Well, the probability of drawing a red card then would be the number of red cards that we have. There are 26 red cards, since half of our cards are red out of the 52 total that we have. The probability of drawing a jack, we know that we've got 4 jacks, so that would be a 4 out of 52. And we need to subtract how many red cards we have that are also jacks, which would be 2 out of 52 cards that we have that are red and jacks. Therefore, the probability of drawing a red card or a jack would be 28 over 52. And we're all set. Let's continue then to part C. We're asked to find the probability that we draw a face card, which we're defining as a jack, queen, or king. Who knew that an ace was not considered a face card? That blew my mind. But we're looking for a face card or a diamond. If we rewrite that again with our terminology, we're looking for the probability of a face card or a diamond, which means again the first question we need to ask ourselves is, are these two events disjoint? Looking again at our sample space, let's highlight the two events we're discussing, a face card or a diamond. And as we take a look, we do have some overlap here. These two events do share some outcomes in common. As we see, the jack, queen, and king of diamonds creates some double counting. Therefore, we do not have disjoint events, and we have to continue with that general addition rule. Which means to find the probability that we have a face card or a diamond, we're going to find the probability of drawing a face card. We're going to add that to the probability of drawing a diamond, and then we're going to subtract, of course, the probability of drawing a face card that is also a diamond. From our sample space, the probability of drawing a face card would be 12 out of our 52, since we have 12 face cards. The probability of drawing a diamond would be 13 over 52, since we have 13 diamonds. But we need to subtract where those outcomes were shared in common, and we have 3 face cards that are also diamonds, so that would be a 3 over 52. Therefore, the probability of drawing a face card or a diamond would be a 22 out of 52. And we're all set. So let's take a shot at our next example then. We're told, suppose that a pair of dice is thrown. They want us to define event E, that the first die is a 2, and event F, the sum of the dice is less than or equal to 5. Now, to be a bit clear with our sample space, the first die being a 2 means we're saying that, okay, as we roll these things, we have to see one of them stop before the other, since we can't physically watch both of them stop at exactly the same time. So event E would be that the first die is a 2. So let's go ahead and highlight that event E to be clear. We've got event E one more time being the first die is a 2, and then F would be the sum of the dice is less than or equal to 5. So we're going to highlight event F to go ahead and give us that visual, and we've got our two events labeled out. Now we're asked to find the probability of event E or F occurring, which means again the first thing we need to ask is, are these two events disjoint? And of course they are not, since we see that the two events share 3 outcomes in common, which means we again have to account for double counting. So like we've done previously, we're looking for the probability of E or F, but since they are not disjoint, that means we need to find the probability of event E occurring, add that to the probability of event F occurring, and then subtract when both E and F are occurring to avoid our double counting. Well, the probability of event E occurring means that let's look at just event E. And it looks like we've got 6 outcomes in event E out of the total 36 outcomes, which means the probability would be a 6 over 36. Now the probability of event F means let's look at just event F. It looks like we've got 10 outcomes in event F, so our probability would be 10 over 36. And finally, subtracting for our double counting, we've got 3 events that occur in both E and F, 3 shared outcomes, therefore we need to subtract 3 over a 36 to account for the double counting, and our probability of event E or F occurring would be a 13 over 36. And we're all set. So we're asked, what is the general addition rule? Based on our examples, are we able to derive that? The general addition rule, and a powerful thing here, is for any two events, meaning if they are disjoint or not disjoint, it doesn't matter. For any two events, if we're asked to find the probability of event E or F, we can split up that E and F, meaning we can find the probability of event E occurring by itself, add that to the probability of event F occurring by itself. We just have to make sure we account for the double counting. So we subtract the probability of E and F occurring. Note that the probability of E and F occurring denotes the intersection of events E and F. That is where both events occur simultaneously. That takes us to our next objective, where we're going to discuss the complement rule. The complement rule opens the door to finding some probabilities when we don't have all the information, and finds us a little bit more efficient of a path when available. We jump right into an example. According to the American Veterinary Medical Association, 31.6% of American households own a dog. What's the probability that a randomly selected household does not own a dog? Well, we know if 31.6% of American households own a dog, then the rest of them do not own a dog. So all we need to do is find the other side of the coin. So the probability that a randomly selected household does not own a dog would be 1 minus the probability of someone owning a dog, which would be 1 minus the 0.316 that they give us, and that gives us a 0.684. Let's continue that to our next example then. We're told the data to the right represent the travel time to work for the 393,186 residents of Hartford County, Connecticut. First, we're asked, what is the probability a randomly selected resident has a travel time of 90 or more minutes? Which means they've established what category we're looking at. We look over at the table and see that of 90 or more minute commute, there are almost 5,000 residents that drive that long. So the probability that a randomly selected person drives 90 or more minutes would be the number of residents that have that long of a commute over our total number of residents. That would be a 393,186, which gives us a probability of approximately 0.012. Now part B is asking us to build on to part A a little bit. We're asked to compute the probability that a randomly selected resident of Hartford County will have a commute time less than 90 minutes. Less than 90 minutes, of course, creates multiple categories. It's all the categories besides the 90 or more minute mark. So we could find the probability that a randomly selected person drives less than 90 minutes by adding all those frequencies up and then dividing by our total. However, instead of doing that, we can just use the information we found in part A by looking at the category of 90 or more minutes. Because what we've established are two options. The probability that someone drives less than 90 minutes would be the complement of the probability of someone driving 90 or more minutes. And we already found the probability of someone driving 90 or more minutes, so we simply need to do 1 minus our 0.012, and we get a probability of a 0.988. So let's continue with another example then. We're told, let's go back to drawing a single card from the standard 52 card deck of cards. What is the probability of not drawing a king? So previously, we were told what's the probability of drawing this or that, and this time they've reversed it on us. They're just saying the probability of not drawing a king, which means we're going to try to find the probability that the card we pull is not a king. Now we can go back to the sample space to look at this visually. Remember, we're looking to draw a card that is not a king, which means we're trying to find the probability of drawing all the cards besides the king. Which means logically we definitely could count how many cards that is. However, it typically flows naturally to say, well, why not just find out how many kings there are, and then the probability of that occurrence leads us to the probability of not drawing a king, which is the whole idea of using the complement. That is, the probability of drawing a card that is not a king would be the complement of, so you see us doing our 1 minus again, the probability of drawing a king. Well, we know the probability of drawing a king would be 4 over 52, since there are 4 kings out of our 52 total cards, which means the probability that we draw a card that is not a king is simply 48 over 52, and we're all set. And that takes us to our conversation about the complement of an event. The complement of an event, which we call EC, would be all outcomes in the sample space S that are not outcomes in the event E, where S denotes the sample space of a probability experiment and E denotes some event. You see the visual representation. We're going to have some defined event E, and the complement is simply the outcomes that are not in E. Now, based on our examples, we are asked the question, what is the complement rule? The complement rule would be, if E represents any event and EC represents the complement of E, then that means the probability of the complement occurring, that is the probability of E to the C, would be 1 minus the probability that event E occurs. And we have our complement rule. And thank you again for joining us.